Okay. So binary search trees, in short, we can use BST. In fact, binary search trees or search trees are the main uses of binary trees. And binary trees, every child. So what is a binary tree? Every child is either a left or every child is either a left or a right child, because every node has got at most two children. Every node has at most children. So that is a binary tree, not a binary search tree, okay? But binary tree is most, I would say the most common client of a binary tree is a binary search tree. So what is the context of binary search tree? So the general abstract data type here that we want to define is an ordered dictionary. So again, the basic idea of dictionary is what? When you are opening the dictionary, what are you looking for? You're looking for a word, right? But why are you looking for a word? Because you want to know the meaning of the word. The word itself is acting as a key, right? So in an ordered dictionary, you have a key, and the meaning is like a value. Same principle. So that's why you can call it an ordered dictionary. So, so definition of this would be a dictionary in which the key has a total order. And the main operations that we would like to perform, of course, when it comes to just dictionary, the main operation we perform is just look up, right? You try to find. But in general, for these data structures, the main operations we are interested in is insert, remove, and find. So these are helping us construct the data structure, and this is helping us in finding something. Therefore, most of the time we have to ask ourselves this question: how costly are these operations? The goal here is to the goal here is to quickly find an entry. Okay, so quickly find an entry. Now, is the quickly part going to be executed in binary search tree or not? We have to explore. I'm not going to answer it right away, but we're going to see. But some of the prominent features of the binary search tree, let me just list down upfront what this data structure allows you to do, which you don't find easily in other data structures. One is that it is easy to locate min and max key. To be precise, locate the node, because after all, The answer we are looking for generally, like when you're looking for something, you're looking for some entry value, right? But what you are wanting to get is the node itself, you know? So it's easy to locate the node with min as well as max key. Why it is important? Because we are going to see that there are certain data structure later on we will learn, like heap, for example, where in one kind of a heap, you can either get min or max easily, but not both. But binary search tree is allowing you to get both min as well as max key with similar amount of complexity. So again, like whether it is quickly or not, we are going to explore, as I said. I'm not going to comment right now. All right. The second important offering of a binary search tree is something like this. When you are looking up a word in a dictionary and you don't exactly know the spelling of that word, you kind of know roundabout. So how do you find such a word when you don't know exactly what that word is? Even in Google search, you have seen, even when you are not spelling the word correctly, Google can figure it out. That, okay, did you mean this, right? It's almost like that. So this ability to find inexact match is one of the greatest or the most interesting features of a binary search tree. Okay. All right. So now what is the binary search tree? So binary search tree invariant is as follows. For any node, so first of all, binary search tree is a binary tree, right? So a binary tree that obeys this binary search tree invariant, that is a binary search tree. It has to obey some special property that makes it a binary search tree. So for any node n, every key in the left subtree of n is less than equal to n's key, and every key in the right subtree of n is greater than equal to n's key. Okay. So what would be an example of this? So let's try to pick an example. So 20. So whatever I'm putting inside the circle, which is representing a node, without my necessarily calling it out, would mean the key. Okay. We already kind of defined that key is something very special to that node. That node may store many other things, but key is something special because using the key, we can search after that node. Okay. So what is the property? If you take any node, on the left hand side, the key values of the entire subtree has to be less than the key of this node, right? So what can we put here? We can put here 10, no problem. Okay, on the left side of 10, what can we put? Maybe we can put 4, because 4 is less than 10. On the right side, I have to put something which is greater than 10. So can I put 50 here? Because it is greater than 10. Any suggestion? Would it be wrong to put 50 here? Because the property is that every key in the right subtree of n is greater than the n's key. So would 50 would be fine? Anyone? You would have to unmute yourself.
No, because 50 is larger than 20.
Correct. So because this, we are talking about this entire subtree, no elements can be greater than this 20, right? So 50 is not possible. So we can choose 15, which is fine. And then on this side, I can choose 12 is fine because 12 is greater than 10. And here I can put 18, which is also fine. I can put here on the right side 14, which is also fine because 14 is still less than 15, but 14 is greater than 10, which is fine. 14 is less than 20, which is fine. And then here you can have 2, you can have 3. So both 2 and 3 are less than 4, so it's perfectly fine. And on this side, I can have 28. And then I can, on the right hand side, you can have 30. I can have another 30 because it's fine to have duplicate, no problem. And that is why we have less than equal to. So the keys can be duplicated as far as the binary search tree is concerned.
Pardon me, how would you add 13 to this tree? Would you have to reshuffle the entire tree?
How would I add this 30?
13.
13. We are going to talk about all the insertion
Okay.
shortly. Okay.
Thanks.
Okay, so this can be 60. No problem. So now you can see, take any node. Let's say if I take 10, right? So whatever is there on the right subtree, whatever is there on the right subtree is greater than 10. And whatever is on the left subtree, that is less than 10. And likewise, if we could take 20, whatever we have got on the right hand side, they are all greater than 20. Okay, so this is the key property that makes this binary tree a binary search tree. Any question on this? Because this is the most fundamental property that we have to keep in mind while we are navigating through the binary search trees. No question? All right, so now we are going to get into traversals of binary trees. So binary search tree traversals. So you already saw the pre-order traversal. So if I have to define a binary search tree node, so how would I define BST node? What should I put inside here? Can you help? Now you should be very good in figuring out how to define the nodes, right? What is there inside the node?
Isn't there a key value and then pointers
Okay.
to the previous node and the next node?
So there is key value. So let's go one by one at a time. So key. So minimally there is a key K. I'm putting this as key purposefully, that this type of the key can be anything, right? And there could be some value V. Okay. And then what else you said?
So the pointer to the sibling node and then the parent node.
Yes. So that was the
Sorry, the
general
left and right.
definition. Yeah. So in this case, I just care about the left and the right child, right? Because there are at most 2 children, right? So what should I write here? BST node star left and BST node star right. Storing the parent is optional. Okay. It's not necessary. It depends whether you want to have for easy navigation to the parent, but it's not necessary. Okay. So if I have to traverse pre-order here, how would I write down pre-order traversal? So what is pre-order here? I want to visit myself first before visiting my children, right? So what code would I write here? What is the first thing I should write? So this I am writing with respect to, let's say, BST node : okay. What should I write? What is the first thing you do in pre-order?
So you visit the do the visiting function and then you move to the
Exactly. I'm visiting myself, right? Which means I'm performing something with my attributes, something involving these key values. I'm performing something, some operation involving these. Okay, and then after that, I check if left is not equal to null pointer, then I go left pre-order, right? If right not equal to null pointer, I go right. I'm done essentially. Okay. If I have to just do the sorry. Let me just make copies of this guy. Okay, move it here. It's going to save some time. Okay, let's do some erasing. I don't want this. I don't want this. I don't want this. And I don't want this. I don't want this. Okay. So what would I need to do if I have to make it post order traversal? So let's just define here. So pre-order meant I am visiting myself. So myself being the root, and then I recursively visit the left and then right. Root, left, right. Post order is I'm visiting left, right, and myself, the root, because I want to visit myself last. So what do I have to do here? I just take this and just move it here, and I'm done. So this becomes my post order traversal. Okay. What is in order traversal? So we said that the in order traversal was undefined for the generalized tree, but it is very useful for the binary search tree. So in order, as the name suggests, it comes in between. So you traverse the left subtree recursively, then you traverse yourself. In other words, traverse this node. Traverse meaning the visit, call to the visit. So root and then right. So it comes in between. That's why it's called in order. And you can see now why in order is undefined for arbitrary number of children, because you don't know where to place the root in. That's why it is undefined. So this is in order. So here, all I have to do is I erase this visit and I just take this and I just move this up. Okay. And then I come here and I visit in between, and my in order traversal is done. Any question? Okay. Now, very important. What happens when you visit in order? So let's try to visit these guys here. So let's visit. So how would the pre-order traversal look like here? If you were to visit and then print, so visit in the sense here visiting would mean just print the content of the node. So pre-order. So first I'm visiting. So it starts with the root node. Everything starts here. So it starts with 20. Then I visit the left subtree, which is 10, the subtree beginning with 10. So when I come to this subtree, then I visit again the node itself. So it prints 10. And then it visits the left subtree of 10. So it comes to this 4, 2, 3. So it finds 4. So it prints out 4. Then again, it's come down to the left subtree of that. So it comes down to 2. So it prints 2. Then the left subtree of 2 is null. So there is nothing to visit on the left hand side. So so after printing 2, then it tries to visit the left subtree, right? So but there is nothing to visit, so it goes to the right subtree. So in the right subtree, it got 3, so it prints itself, and then looks for left subtree, right subtree. It doesn't have anything, so it's done. It goes back, and then it comes back. So comes back to the node 10, and then now it starts visiting the right subtree, because the left subtree is done visiting. So then it prints 15, then followed by 12, then 14, then 18, and then it is done with the left subtree of 20. It comes to the right, goes to 28, then 30, then comes to the left, which is 30, and then comes to the right, which is 60, and it is done. Now, if I am visiting the in order traversal, how would it look like? So post order, you can imagine. Okay, we'll come to that post order shortly. So first, let's try the in order. So in order is what? You visit the left subtree first, and then you visit itself, and then you visit the right subtree. So with respect to 20, the left subtree, you keep trying to visit the the left subtree first. So 10 has got left subtree, you keep going down. Then 4 has got left subtree, you keep going down. Comes to 2 doesn't have any more subtree, left subtree. So you end up printing 2. And then you go to the right subtree of 2, which is, then it is getting chance to print 3. Now it is done with the printing of the both the, I mean, there is no left subtree of 2, so it's done with the right subtree. It is done with the left subtree of 4. So now it comes back to 4 and prints itself. And then 4 does not have any right subtree to print. So it is done. So it goes back. So with respect to 10, the left subtree is done. So therefore now it is ready to print 10. And then it goes to the right subtree of 10 and comes here, finds 15, but it is not ready to print 15 because remember, in order means you have to go to the left subtree first. So it goes to 12. 12 doesn't have any more subtree, so it prints 12 and then comes back to 15. Sorry, 12 has a right subtree. So then after printing 12, it goes to printing 14. And then after the left subtree of 15 is done, then it prints itself 15. And then it goes to the right subtree of 15, which is 18. And now it is with respect to the node number 10, or with respect to the node with the key 10, it is done with the left subtree itself and the right subtree. So now it is going to the next node, which is 20. Now with respect to 20, the left subtree is done. The whole printing of this part is done. So now it prints itself. So 20, and now it is ready to print the right subtree. So it comes here, it prints 28, then it comes to 30, prints 30, and then prints 60. Now if you notice, this is perfectly sorted order. So therefore, in order for binary search tree is very special because it produces a sorted output. Okay, so how would the post order look like, just for the sake of completeness? So post order traversal. So you start, so post order is that you want to visit the left subtree, then right subtree, and then itself. So with respect to 20, it goes down. So 10, 4, 2. Okay, it has nowhere to go, right? It cannot go further to the left. So it is now going to start going to the right, which is 3. So it will first print 3. And then after the children are done, then it is going to print 2. After 2 is done, then it is ready to print 4. So notice that it's going to always print the children before itself recursively. So after the 4 has been done, now it is not ready to print 10 yet, because all it has done so far, it has printed the left subtree with respect to 10. So now it is going to try printing the right subtree. So it goes to the right hand side, it finds it's 15, but it's not ready for printing 15. So it goes to the left subtree, which is 12. So 12 has got further right subtree, so it goes to 14. And after printing 14, now it is ready for 12. And after printing 12, now it goes to the right subtree of 15, which is 18. And then it prints 15. Okay, at this point, it is done with both the left and the right subtree of 10. So now it is ready for printing 10. So now it is done with the left subtree of 20. And now it is ready for the right subtree of 20 before printing 20. So it goes to 28, but it's not ready for printing 28. It goes down 30, goes to 30, and then 60. So it goes to print 30, then 60, and then 30 again. Okay, interesting. The two 30s are not placed contiguously in the post order. And then it comes to 28, because it has printed all the children of 28. And then now the left subtree and the right subtree of 20 are done printing. So now it is ready for printing 20. Any question on this traversal? Okay. Okay, but the most important message that we delivered just now is that the in order traversal of a binary search tree is very special. So in order traversal of a binary search tree visits nodes in sorted order. Okay. Okay. Now we are going to start going one by one, figuring out how we are going to perform those three fundamental operations that we talked about. Find, then remove, and search. Sorry, not search. What did I write? Find, insert, and remove. These are the main operations that we are concerned with. Okay. So let's start with find. So find, what are we trying to find here? Who can tell me? What operand the find should take? Any volunteer?
Some key.
Exactly. Very good. So it's going to take key as a parameter. Okay. How do you find something in binary search tree? Finding is very, very straightforward. So suppose I'm looking for 15. What would I do? Because of the property that is there for any node, every key in the left subtree is less than the key of n, and every key on the right subtree is greater than n's key. So therefore find is just going to exploit that property. So if I'm going to find 15, so I'm going to ask, so with respect to the root node, which is 20, is 15 less than or greater than the key of this node where we are starting, which is 20. So 15 is less. So I'm going to go to the left subtree. Then I'm hitting 10. I'm going to check, is there a match? Okay, first thing is that it's going to check whether it's a match or not. When it's not a match, then it's going to look whether it is less than or greater than. Very similar to the binary search algorithm. So here, it's going to ask the question. So when it reaches the left subtree, the root node of the left subtree, it asks the question, is there a match? If it is not matching, then I'm asking the question, is it less than or greater than? So 15, if I'm looking for 15, 15 is greater than 10. So with respect to this node, I need to now traverse to the right. I come here, then I look for match. Is it matching? Yes. So I'm done. So it is not very interesting to talk about find. It is pretty straightforward. So finding is just follow the binary search tree invariant. Okay. But what is more interesting is, as we talked about, is inexact match. So let's talk about that. So what is an inexact match? So the problem is to find the smallest key that is greater than equal to k. So this find we are going to now see more from the light of the inexact match, approximate match. Okay. So perfect match is easy, we just saw. But inexact match, how are we going to find? So either we are finding the smallest key that is greater than equal to k, or find the largest key that is less than equal to k. So what is the strategy here? When searching in the tree for a key k that is not in the tree, we encounter so when we are trying to find something which is not there in the tree, we encounter actually both the smallest key greater than equal to, so we encounter both the smallest key greater than equal to k and the largest key that is less than equal to k. Okay, let's try to see what this means. So suppose I'm looking for let's say 26. Okay, so if you have to find 26, let's say I'm looking for, okay, fine, let's try 26. So in order to find 26, what did we have to do? We have to come here and then we looked for 26 on the right of 20 because 26 is greater than 20. Okay, we found 28. Okay, and then we are finding that 26 is less than 28. So I'm wishing to visit the left subtree of 28, which does not exist. Correct? It tries to visit here to locate 26, but there is no left subtree. So it ends there. The search ends there. So what did you see here? In order to find 26, it had to hit the greatest key that is less than 26, which is 20, and the smallest key that is greater than 26, which is 28. So in other words, 26 is in between 20 and 28. So before giving up, looking up for 26, it had to visit both 20 and 28. But when did it give up? So the last node where it traversed to the right, last node from where it traversed to the right before giving up, that is going to be the node with the largest key less than that number that we are looking for. And whichever node with respect to which after going to the left and giving up, that is the smallest key that is greater than that number. Is that clear? Is that point clear? Any question on this point?
Wait, so after it says we can't find it, like, does it return something or what does it do? It just ends the program.
No, if you are looking for an inexact match, right? So this find can have two varieties, right? Either you're finding for exact match or inexact match, right? If you're opting for inexact match, right, So if you're looking for exact match, if you don't find something, it's going to return null pointer, right? So this is going to return null when not found, right? When you're looking for exact match, correct? When you are looking for inexact match, right? Then it's okay. You are wanting to give some approximate value. And the approximate value we have defined here. The smallest key, so you're able to now return two different values. The smallest key that is greater than or equal to k, and the largest key that is less than or equal to k. Okay. In other words, if you're looking for a node, let's say you're looking for k value, right? You're encountering two nodes, k1 and k2, right? It is now capable of returning k1 and k2 instead of giving up on k. Is that clear?
Yeah.
Yeah. So inexact match is just allowing you to not give up, but give an approximate match within whose range that particular node belongs. Okay. So how do you find that? So last time you went to, instead of writing, you went to the right. Last time the search went to the right is going to give us what? Last time you went to the right is going to give us what? What? The largest key, that is less than or equal to k, right? Let's note down one more time. Here we were looking for 26, right? To find 26. You gave up after going to the right from 20, right? So this was the largest key possible, that is less than 26, right? That's when you gave up on turning right. Okay. And the smallest key, likewise, is last time the search went to the left. Both before giving up on the search. Okay, isn't this very cool to be able to find this? Okay, so apart from finding either exact or inexact match, right? And apart from doing insert and remove, which we are going to visit shortly, we said that another key characteristic of a binary search tree, which is very unique, is that the same representation is allowing you to find the minimum and the maximum. The node with the minimum value of the key, or yeah, the node with the minimum value of the key and the node with the maximum value of the key. What do you have to do in order to find out the node with the minimum value? You can see it here. You keep going, traversing the left pointers, right? You keep traversing the left pointer till you hit null. That is going to give this is the minimum value. And if you keep going right till you hit the null pointer, this is the max So in the same data structure, in the same arrangement of the data, you are able to find out min and the max. Okay. So it's pretty straightforward to find the min and the max. So node star min is to find the node with the min key, and node star max is to find the node with the max key. Okay. So what do we do here? Of course, if the tree is empty for all of these operations, you're going to return null. I am not explicitly mentioning that. That's a given. So this is essentially you repeatedly go to the left child until hitting the null pointer. And likewise, this is going to be the rightmost node before hitting the null pointer. All right. Now we come to two important operations: how to insert and how to delete. So node star insert. So here you may ask, why are we even returning any value for insert? So insert is straight away we are giving some key and we are giving some value. That's what we are constructing the node with. And then we are inserting into the binary search tree. And whatever we have inserted, that node, that newly created node is what is returned by the insert. Okay. So what do we do here? You follow the same path through the tree as find follows. Because in order to insert something, right, in order to find the right position, what do you have to do? You have to keep looking for what you are trying to insert till you hit a null pointer. So here, obviously, when you are looking for find here, we are talking about the exact find. Okay, this is an exact match you are looking for. So you're looking for an exact match. Okay, so in other words, you are looking for an exact match. So you may or may not find the value. If you find the value, fine, then you just make with respect to that node a left child of that node. Even if you make the right child, that's also is fine, because the property is just saying the left subtree should be less than equal to, and the right subtree should be greater than equal to. So it does not matter whether you are placing the node with the same key value either on the left or on the right. It really does not matter. Okay, so when the search reaches a null pointer, okay, then you replace the null pointer with the pointer to the new node with new node constructed with the key and value pair. So obviously you can think of, like, when the key and value pair is there, you're constructing the node first. And then you are talking about inserting in the binary search tree in the right place. And in order to insert, you are trying to find, and when you're reaching the null, you're just replacing the null pointer with the new node. Okay. Since the duplicate keys are allowed, so therefore you put, so in the case when duplicate key is present, so put the new node in the left subtree of the old node with the same key. Is that clear how the insertion is happening? Any question on the insertion before we move on to remove?
Yeah, I have a question.
Yeah.
It will, so the insertion will always work out such that the new node will never have any child nodes.
New node will never have a child node because you can see when you are inserting, you are giving up somewhere. Because your giving up is based on either traversing either left or right and finding a null pointer, right? That is the way you are giving up. So suppose you want to insert 17, for example, okay? So let's see where you are going to give up. So you come here 15, right? So then 17 is falling in between 15 and 18, correct? Right? So you will find, okay, 17 is greater than 15. So you move to the 18th, the node with entry 18. And then 17 is less than 18. It's a null pointer. So you just replace here 17. Do you see this? Because
Okay, yeah, that makes
end
sense.
of your end point is always hitting a null pointer. That's the key. So you will always find a place to stick the node in. Okay. Now we are at a home stretch in terms of the operations we can perform with the binary search tree. So this is remove. So node star remove. So when we are removing, what are we passing? I want to remove a node with what? What should we be passing? How do we ask that I want to remove something from the binary search tree? What is it that we're going to pass in to say
A key?
remove this? Exactly. So you're now getting used to this, that every transaction with respect to the data structure is keyed off a key. You know, so
But
every
what if it's a duplicate? Then like,
yeah, you would have a strategy of either removing every single key with every single node with that key value, or you may say whichever node is first encountered. So it depends on the problem, right? So suppose you want to remove 30, right? If the strategy is to just remove one such node containing 30, then whichever you are able to find first, that's what you want to remove. But if the strategy is to remove every single node containing 30, then you would have to keep running till you hit the find coming back with saying that, okay, I don't find any more 30. Is that okay?
yeah, but so like if you remove the first one encountered, right?
Mhm.
Then wouldn't you have to kind of reconstruct that subtree? So
Yeah,
like,
we are getting there, how remove works, okay? So remove is actually the toughest of all these operations. You could see that others are pretty straightforward operation. So remove has got bunch of cases that we have to consider. Okay, so first step obviously is to find. So find a node n, okay, with key k, because that's what we have to do. First, we have to find. And this is going to return null if k is not in the tree. So when I'm using the term find, if I'm not saying anything, that just means exact find, right? Exact match. We don't even have to think about whether it's inexact or not, because inexact is a very special sort of offering of binary search tree that we already established. But find typically just means you look up for the node. If you find it, then return that particular node. If you don't find it, then you return null pointer. Okay. Therefore, if k is not in the tree, then it's just going to return whatever find has returned, which is essentially a null pointer. Okay. So now here, let's talk about what are the possible cases that can arise for removal of a node. So first case is that the node n that you have found that we want to remove, right? That n has no children or 0 children. It has no children. So what are we going to do? So if you have a binary search tree, so what would be an example of, in this case, 1, 5, 6, 7, sorry, I'm not maintaining the binary search tree property. Let's see. This is 8. This is 7. This is 6. Okay. And this is, I'm sorry, 9. This is 9. Let's go step by step. Suppose this is 8. This is 10. This is 9. This is 12. And this is 5. Okay. Suppose we have a tree like this. Okay. And let's say this was on the left side. So this could be something that is greater than 12. So we can say 15, let's say. Okay. And it has got other things going on. Okay. So first condition is that n has got no children. What are the example of nodes in this particular tree that has n has no children? Which nodes do you see that n has no children?
5.
5, 9, and 12, right? So suppose you want to remove 9. So you can see the removal of 9 is so easy. Actually, I should have drawn it. Let me just. Okay. Let me just duplicate this, it's easier to show. And then let me just do some erasing. Okay. So suppose I want to remove here the key with 9. So all I have to do is just detach it from the parent. So detach from the parent. So detach it. So detach it meaning n. So n is here 9. So this is what we are interested in removing. So we are interested in removing this. So when we are removing this, all we have to do is detach this from the parent. So now this points to null. So it's fairly easy. Nothing.
I
Go
have
ahead.
a question.
Go ahead.
So the node that we have doesn't have the parent anymore. So how are we able to go back up the tree from find, which returned 9? Like, how do we know where 10 is? Because it's a one-way path.
So remember, we had the option of having parent pointer, right? We said that. So especially for removal, if suppose you're only constructing the binary search tree and you're not doing any removal, right? Parent pointer is not necessary, correct? But when you have to do a removal, having a parent pointer is handy, and therefore you would maintain a parent pointer.
Okay.
Okay. And another, okay, let me give you another answer. So before coming here, right, you can on the way maintain the parent pointer, right? Whichever node you visited just before coming here. That's another way. So it's still an option. Either you maintain or you maintain along the way. Then you have to keep an auxiliary variable to track the parent as you are finding. But otherwise it's fine. It's going to work. Is it okay?
Yeah, thank you.
Okay. So the next possibility is that n has only one child. So this case is also fairly easy. So here, so this case, what do we have to do? So what would be an example of a node with only one child? So say we want to remove which node? Actually, there is nothing here which has got only one child. So let's create one, okay? So say this, I think it's easier to create here. So let's say you have 4, okay? So here, if you say remove 5, so 5 has only one child, right? So this case is also fairly simple. All you have to do is that you have to move. So if you have this, then move the nth child up to take nth place. Take a copy of this guy because otherwise I have to keep erasing. Okay. Okay. So now you can see if you have to remove 5, what you have to do is so here we are deleting 5. So we have to just make the 4 take the place of 5, right? So we can say that this becomes 4. And actually, this doesn't exactly represent. So what should happen here is that so this node 4 is going to just occupy the place of 5, and 5 gets disconnected and removed. Okay, so these are easy cases. Now here's a tough case. The tough case is when n has 2 children. What do we do in that case? So here is a strategy. So let n2 be a node in n's right subtree. with the smallest key. In other words, right subtree means you're trying to find the largest value that is the smallest value that is larger than n. Okay, that's what you're trying to find. So after you do that, then the next step is that remove n2. So you would remove n2 because that n2 will have either of these two above two configuration. Either it has got only one child or no child, because it's easy to remove. So n2 has no left child, right? Because on the right subtree, you're looking for the smallest key. Remember that when you're looking for the smallest key, you keep walking down till you hit the null pointer. So it will be a child with no left child. And therefore, easy to remove. So we are, instead of trying to remove n, which has got two children, which is more complicated, we are trying to find something else to remove, which is easier to remove. And after we have done that, we just replace. So notice here we are replacing n's key. We are not replacing the node. We are replacing just the key with n2's key. That's all we are doing. So let's see how it is working here in this example. Okay. So what would be an example here? Remove with the two children. So suppose you want to remove 8. 8 has got two children. So 8. So what do? We go to the right subtree of 8. So on the right subtree of 8, we find the smallest key. So which is, if you keep traversing from this root node, which is 10, you find the smallest key is the leftmost child, which is 9. Okay. So this 9, because the range is such that the 8 is, there is nothing in between 8 and 9. That's the key, right? There's nothing in between 8 and 9 in this whole tree. And therefore, you are able to conveniently utilize this key value in here without changing any binary search tree property. Because there is nothing in between this range in this binary search tree. That's the key. So nothing in between. Okay. So because of that, now what you have done here is that you've got this, and from here, your focus is going to your focus is going to 9. Okay, 9 I know how to delete because I just saw that if you have 0 children, great, it's so easy to remove. So I'm going to remove 9 because it's very easy. And I can just substitute the value of 8 by 9. The value of 8 gets replaced with the key that of the node that got deleted. And this becomes null pointer. This is a very, very smart way how the case where the two children are involved is taken care of. Any question? There was the only complication that is involved.
Yeah, I have a question. I guess this would be less efficient, but couldn't you also just call the insert function on the right child and then the left child? And then I guess like the second part of that question, why do you lose anything by putting 9 where 8 is instead of putting the 10 where 8 is and then putting the 9 below that, like kind of extending the left arm?
So So essentially, so we have to remove 8. So can you tell me the step by step, what is the first thing we should do? So the goal is to remove 8. Okay. So what is your first step?
The first step is to replace the key with the key of the smallest number on the right subtree.
Okay.
Yeah, which is 9. But I guess my question is, do you lose anything by having 10 be a branch of what is now 9 instead of just kind of bumping the 10 upwards?
Question is that how do you bump 10 upwards? Because you may have the situation where suppose in this case it was not 9, it was something else, and then you have a subtree going down, because this is, you can remember, this is like we have to go down the leftmost chain to the end, right? So this could have been, suppose this is 7, sorry, let's say the way the numbers have been chosen, my point you're getting, right? So this could have been this number, right? So you have something here. So you're deleting actually this, suppose, right? So how are you going to transport 10 over there if it has already a left child?
Could you not just insert the right child of 8 and then insert the left child of 8 in like the revised subtree or in the revised?
So the thing is that if you place 10 here, you have to justify what happens to the rest of the left subtree of 10, right? Because it has to be less than, you cannot place on the right side, correct?
Yes, but it'll always be less than the, or any of the right subtree of 8 will always be less than any number on the left
Correct.
subtree of 8. So wouldn't it still work?
You have justified this part, okay? There is no problem in getting this guy here, right? With respect to this side, right? What about this guy, like whatever is here, you know? Because there is still subtree here, right? There is still subtree here. So you have to think about where this subtree goes, right? And where this subtree goes, correct?
Okay. Oh yeah. I mean, I see. Oh, I see what you're saying. I guess what I was kind of just saying is like,
Yeah.
Instead of like literally moving, swap the
Yeah.
key of 10 to where 8 currently
Right.
is.
Because to move the node is not so straightforward, because you're dealing with many other pieces of the subtree that you have to adjust and really talk about how you are dealing with it. Is that clear?
Yeah. Yeah. I guess that makes sense.
Yeah. Okay. So overall, I mean, although the thought that you had is a great thought, which we are going to exploit in the what is called splay tree, which we are going to cover next week. I'm not going to go into today. Although I had originally planned, but I want to, it's better to get the concepts sink in rather than just rushing through it. So now at this point, I would like to just wrap up this whole thing by talking about running time. Okay. So far, it seemed like the running time should be fast. That's why we are discussing this data structure, right? Otherwise, why discuss about this? But the truth is that this running time for a binary search tree for all these operations, insert, remove, find, they can be efficient only if you are lucky. So what I mean by that is that suppose I have what is called a perfectly balanced binary search tree, which looks like this. This looks very nice and balanced, right? So this is, it's a perfectly balanced binary search tree. So if you have a balanced binary search tree, if you see how the mathematically the the number of nodes follow is something like this. If you have a single node, right? So if you try to jot down number of nodes here and number corresponding to the depth of the tree, right? So if you have only one node, right? Remember what is the depth of that? What is the, do you remember what is the definition of depth? It is the path to the deepest descendant, right? And you're trying to find the number of edges. Remember, that's how we define. So depth is 0 here, right? Here you have one node. Correct? If you have 3 nodes, this is kind of fairly complete binary tree with 3 nodes, right? So if you have 3 nodes, the depth is 1, because the deepest descendant is this, and the number of edges, right, from the root to the deepest descendant is 1. Okay, let's keep going. How many nodes are here? How many nodes?
7.
And the depth?
2.
2. So you can see it's nicely following a formula. So if the depth is d, then the number of nodes is 2 to the power d plus 1 minus 1, right? So when it is 2 to the power 3, which is 8, 8 minus 1, 7. Okay. So that's the relationship between the depth. So number of nodes is equal to 2 to the power d plus 1 minus 1 for a perfectly, so this is called perfectly balanced binary search tree. Whether it's binary search tree or binary tree, that is irrelevant, because these are just nodes. Binary search tree we discussed is just that property. So what do we learn here? That no node has depth that is greater than log base 2, log of n base 2. Now, why is this important? Because now when we talk about running time, so running time of every single operation, right? Every single operation, insert, find, remove, min, max, all of these operations we discussed. For every single operation, the time was proportional to the depth of the deepest node visited, right? Is it not? And therefore, if no node has got depth greater than log of n, therefore the running time should be log of n. But log of n for what? Log of n for perfectly balanced binary search tree. Is it really true for binary search tree? So this is the key point we wanted to reach at. So what happens if I want to insert these nodes 1, 2, 3, 4, 5, 6, 7, and so on and so forth? The numbers are coming in this order. So first we insert 1. Second, 2 came, 2 is greater than 1. We inserted 2 here. Then 3 came. We kept looking for, okay, finding 3 could not find here. So 3 got inserted here. Then 4 came, 4 got inserted here. Then 5 came, 5 got inserted here. Then 6 came, 6 got inserted here. 7 came, 7 got inserted here. You see where it is going. It hardly is looking like a tree anymore. It's more looking like a linked list. So in the degenerate case, the most degenerated case, essentially it would appear like a linked list, right? And therefore, the worst case running time for the binary search tree for all of these aforementioned operations is order of, what is it? The worst case running time for binary search. What?
Of n or a d, like the entire depth.
Not D. That's the key. Yeah. You can say that this, in this case, the D is, you can say, yeah, that's correct. It's order of n. So we did not get so much of value out of all of this discussion, correct? Why we discussed so much, and at the end, all we got is the searching complexity is just order of n and not order of log n. So that's why the discussion does not end here. So we have to discuss other forms of binary search trees, other forms of binary search trees which are more in a balanced form. Like there is AVL trees. There is what is called red-black trees. There is splay trees. So these are all different varieties of data structures that are based on binary search tree, but they try to maintain the balanced property, because the key here to get a very efficient running time for all these operations is to produce this kind of structure and not degenerate into this linked list sort of a structure. And therefore, the topic that we're going to take on next week, before the midterm, by the way, there is a midterm. So either I could send a recording of this play tree discussion, or we will have discussion just before the midterm. So, but the key thing is that the next week you're going to have your midterm exam that is going to cover until the binary search tree. Any question?
I'm sorry, Professor. So it's gonna, you said it's gonna cover until the binary search tree, so not including or including it in the BSD.
Including binary search trees, including
Thank you.
trees. Yes.
Could you give us like an overview of kind of what your tests are like, since like we have
Okay.
no idea?
Yeah, thank you for asking that question. What I will do is that I wanted to also share some practice questions, okay, for all the topics that we have covered so far. And maybe, I mean, overall, whatever we have discussed through all these sessions, if you have understood the concepts and applied them through your labs, there will be nothing that should be difficult for you. That much I can tell you. But still, I will actually post some exercises or some basic questions on maybe some recursion for you to practice. Is that all right?
Yeah, but is it like, would you say it's like more multiple choice heavy, or like more like code writing heavy, or?
there will be more descriptive type of question rather than multiple choices here. Because I want to see the concepts essentially come out through these exams. So whatever we have discussed, the focus is not so much on getting the exact syntax right, you know, but I want to see the understanding right. Is that okay?
Yeah.
Okay. So
Actually, sorry, one more request. I've been like messaging quite a few people in the class, and like several people have like, I guess, agreed that like, or yeah, kind of agreed that there should be like, I don't know, some kind of like system to drop a homework or like get a late token system. Because like, I don't know, many people have told me like this is the only class in which they haven't had a late token, especially like for like Comp15, for example, we had several late tokens and like several TAs available like throughout the week. So like we were thinking like maybe it's fair for you to maybe send a survey out to ask people like maybe what would be fairer in terms of like making the course more I guess accommodating for like this structure possibly.
So I want to actually invite Matt to comment on this because he had been TAing for this course. I want to hear his opinion on the late token and whether he himself has tried it out when he was teaching this course before. Matt, would you like to share some?
Sure. I did not use late tokens over the last summer. It's something that is commonly used during regular semesters, but you know, becomes difficult with the number of assignments we have. So it's possible to implement it, but becomes tricky. So, I mean, there's, you know, the question that we're almost halfway through the summer now already, and how many we would have to add. You know, yeah, I mean, I guess we have some infrastructure established to be able to enable that. So part of that, if you'd like to, I could add a late token or two, but then the question would be, you know, how many days does a late tokens usually would cover one day. But if you had like 2 or 3 tokens, you could use a maximum of 2 on an assignment is usually how it works. So you'd have a maximum of 2 days late for an assignment. And of course, this also means that if we enable late tokens, then we have to delay grading by a few days. So you guys won't be able to get your assignments back as fast, because if people are submitting with late tokens, but they've already submitted, I'm not going to be regrading things. So.
Yeah, I think that makes sense to me. Actually, what Matt, you said in the beginning is also one of the core reasons why late token was not introduced, because this course is very fast paced, and also every week you are having the load of labs and homeworks, and on top of that there will be this midterm and final exam. So if you are late, it is going to actually cost you more than anybody else, because you're carrying the extra backlog to the next assignment. So technically it's actually in your favor to not have these. But at the same time, maybe what we can do is, Matt, maybe we can take some feedback, intermediate feedback, to see what others, like overall the class thinks. And then for the rest of the semester, we can accordingly adjust. Would that make sense?
Sure, I would echo that as well. I would really encourage that if we do some kind of late policy that one day should be the maximum,
Okay,
because it's so hard to catch up,
right.
you know, with everything. It's not like we have a lecture on a Tuesday and a lecture on a Thursday and, you know, a lab that, yeah, it's much harder with everything on one day. It's just one of the constraints that we have to deal with. So
Like, could another consideration be like, I don't know, possibly dropping a homework as well? Because like, I don't know, I feel like we put in so much time into it, and like one little error can like crash.
that, in some sense, that's true, but you have to realize that all of your peers are also working very hard, and if we're dropping their work, then
Right.
the work they're doing is not being adequately reflected in their outcome. It's just sort of unfair to them.
Or like, I mean, for other classes, for like Comp11, for example, like it wasn't a mandatory drop one homework. Like you only dropped it if it made your grade better, basically.
No,
Right.
I mean, I understand that.
Like,
but
Let's settle.
I mean, like,
I think you raised another good suggestion, Chris. So basically what I would do is that I'm going to add one more homework. Okay. And basically, just like for the lab, we are choosing the best 9 out of 10. Like that, we can choose the best 6 out of 7 homework, something like that. Is that okay?
Yeah. And like, also, by the way, this is not like I mean, it's my personal opinion, but it's also like I've asked several people in the class. That's, I wouldn't say it's like extremely biased. Like I've asked like 10, 15 people, and like 7, 8 people or more have like agreed with me. So like, yeah,
well, just because it's the student's opinion doesn't mean it holds
yeah,
true. You know, that's unfair to say that, really.
Giving like some like,
you know,
bias.
we have to also, you know, uphold the proper standards of the course to the best of our ability. But you know, we understand things are difficult and sometimes.
So is this reasonable? I'm going to add one more homework, okay? And then let's not worry about the late token, okay? Let's keep that.
I think that's a good idea.
As straightforward as it is. Otherwise, the question still remains that we did not use the late token for the past labs and homework. It just makes things inconsistent. So I think consistency is better.
I agree.
I'm going to just add one homework and then have you kind of have the opportunity to kind of recover in the case like where you felt it was difficult for you to catch up in previous ones.
May I ask a question about that extra homework?
Yes, go ahead.
If I'm like completely okay with my grade at the time of that assignment, can I just not do it? If we're dropping one of the homework grades?
Yeah, as I said,
or like not have to worry about the grade, I suppose.
Yeah, of course.
Okay.
So you're selecting the best 6 out of 7, right?
Okay.
So if you're happy with the 6, then you don't worry about the 7. That's it.
Okay, I guess I shouldn't have said to not do it in its entirety, but like I wouldn't want to get to that 7th homework assignment and worry about it like potentially lowering my grade, I guess.
Yeah, I mean, all I'm saying is that this is just an added favor that I'm able to do, and then you can utilize however way you feel is to your advantage, you know?
Okay, I appreciate that then, thank you.
Okay.
Sorry, I was wondering if I could ask something quickly. I understand if it's not possible, but I'm on quite a different time zone than most of the United States. And I was wondering if you guys would consider at all making it due maybe like 12 hours later, just because I don't know when you guys get around to grading it. I understand if that sort of messes up the schedule quite a bit, but for me, it would allow me to sort of work on it next day instead of having it due in like the middle of the night. And just if I sort of run into a problem.
Sure. So what time do you think it would be better for you to adjust?
So, I mean, it would be, best case scenario would be if I could get 12 p.m. Eastern time, but I don't know if that's difficult.
That is perfectly fine. So we can make an adjustment. So you want that to be Wednesday, 12 p.m. EDT as opposed to Tuesday, 12 a.m. I'm sorry, Wednesday, 12 a.m. You want instead of that
Yeah. So just like 12 hours later than what we have right now. It
That's-
would just make my life a little bit easier and still be.
Yeah, no problem at all for this. Right, Matt?
Okay.
This is for
Right.
the exam, the midterm time? Sorry. Is it?
Oh, sorry. I meant
What
the
was this
homework.
for? Oh, the homework due date. Oh, sure.
Yeah, homework and lab.
Yeah. No, that's no problem.
Yeah,
So-
I'll take that adjustment, no problem at all.
So this is 6 hours prior to class.
Yes.
Okay. Yeah, absolutely. And the same for labs?
Yeah, I'm going to make that
Right.
change uniform throughout the rest of the course.
Yeah.
If you had mentioned that toward the beginning of the course, we would have made that adjustment right away.
Yeah, I was
Yeah.
honestly I wasn't so aware of it, and had to move around. But now just wanted to ask if possible. But thank you so much. That makes it a lot easier.
So I think we have we have a good discussion on.
I have a quick question,
Go
just
ahead.
logistics wise. For the 7th assignment, is that going to be due after August 11th? Like that, would that push things back, or would it
Could be,
still
could
be
be.
everything
Yeah,
before August 11th?
Yeah, it could be. It could
Okay.
be 1 or 2 days after that. That's possible.
Okay, thank you.
As Matt said, right? Like any adjustment we do, it can have some impact on delaying the grading and so on and so forth. You know. Okay. Anything, Matt, you want to add to this discussion, or we are good?
I think we're good. I think
Okay,
we're
good. So
Thank
I'm
you.
going to stop sharing. Maybe you can take over for the homework for today.
I have one quick
Sorry,
question about
okay.
the midterm.
Go ahead.
Does it happen to be open note or no?
No, no open notes, please. And a lot of things are going to be on face value because the understanding is that we are doing it remotely. It's very unique setup. The expectation would be that one should not be going to the internet and looking up for answers. And I mean, of course, the TA would have their own ways of finding if there is any such kind of things done during the exam. So yeah, it is going to be closed note. Okay, Matt, why don't
All
you?
right, sure.